We're going to look at a question now to develop our intuition around speed and acceleration. This question looks at a car that's moving down a road, and the graph that I've shown here plots its position as a function of time. And I've given 4 choices here, and I'm asking which of the following is true. Is it the case that the car is speeding up all the time? Is it slowing down all the time? Is it the case that it speeds up and then slows down? Or is its speed constant? To answer this, we need to actually learn something about the speed or the velocity of this car. And we also need to learn something about the acceleration, because it's asking about slowing down, which is essentially changing in speed, or speeding up, which is, again, changing in speed but in the opposite sense. So how do we learn about what the velocity is doing? It's easiest if we pick some times here. Let's just pick 3. And the velocity, it would be indicated by the slope of a tangent line at this point on the graph. So at this point on the graph, right there, I could draw a tangent line. And that would be the slope of that tangent line would be the velocity at that point on the graph. I could do the same right here. And I could do the same right here. And one thing you notice is that the slope is the largest and then is steadily decreasing. In fact, if I were to draw it even further out, it seems like the slope would be 0. So it's the case that v1 is larger than v2 is larger than v3. And if I were to sketch velocity versus time, it looks like it might look something like this. So in fact, it seems like it's slowing down, so that would be answer B. Notice I've drawn the velocity positive because all these slopes are positive. It's just that they're getting closer and closer. The velocity is getting closer and closer to 0. So this is the best way to look at the problem. And then, since the velocity is changing, we can also ask what's the acceleration doing. And it looks like the acceleration would, again, be tangent lines to this velocity graph. It looks like it would be a negative acceleration, which makes sense. It's a negative acceleration is the case when the speed is slowing down. There's a counterintuitive feature of this graph, which takes some folks a little bit extra time to digest, and that is that the acceleration can be negative even though the velocity is always positive throughout here. The fact that the acceleration has the opposite sign as the velocity merely indicates that the velocity will be slowing down or be decreasing. So it's a little bit like hearing a stock market report where corporate growth might be 5% for this year, and it was 18% last year, and this has analysts all excited because they realize that a slowdown is about to occur. Although the growth is still there and it's positive, it's 5% this year, it's not as large as it used to be, and as a result, they notice a trend that there's a slowdown occurring. In the same way, the velocity at this point on the graph is positive, but it's not as positive as it was over here. And so the acceleration, which is the change in velocity over a change in time, is negative, indicating that the velocity will continue to trend downward toward the origin. Here's another practice problem now of just trying to sketch, given position versus time, what speed and acceleration might look like. In this question, I'm going to throw a ball straight up in the air, such that it will eventually turn around and fall right back down and hit me on the head. I'm not going to throw it across the room, I'm going to throw it straight up. So this graph shows simply the height of this ball as it goes up in the air and comes back down again. It looks like a parabola, but that's only because the horizontal axis is time, and it's not that I'm throwing it across the room, it's just that the ball is going up in the air in time and then coming back down in time. And the question asks, could you please graph the acceleration? Well, we haven't said, we don't have a graph of acceleration here, we have a graph only of position. But we know that acceleration is the change in velocity over time. So we first should look at velocity. Remember that velocity is a change in position over time, or at an instantaneous level is the derivative of position with respect to time. And the derivative is signified graphically by the slope of a tangent line to this graph. So let's draw some tangent lines. I'm going to pick some times here to show on this graph. And there's one time which is going to be particularly convenient for us to look at, and that is right here at the top of the arc. That's because the tangent line here is roughly horizontal. In other words, the slope of that tangent line is 0, and the velocity, therefore, at that time should be 0. Over here, the tangent line might look something like this. So it's got a slope that's very large and it's positive. And as I move along in time, I still see tangent lines that are sloped upward, but less so every time. So what's happening is the velocity is trending down until it gets to 0 right there. And then, of course, at other times, this velocity is now becoming more and more tilted here. The slopes are becoming more and more tilted. But notice that they are negative slopes. They drop down in time for each one of these. So, in fact, the velocity keeps trending down like this. It's a positive velocity here. It's a negative velocity here. Positive velocity means that the object keeps moving in the positive y direction. Negative velocity means that it's moving in the negative y direction, which is more or less what we have graphed there. So this is a way of getting the velocity curve from the position versus time. Now, what does that have to do with acceleration? Well, remember that acceleration is the change in velocity over time, which, of course, at the instantaneous level is a derivative, dv dt. If I were to graph the acceleration, this being time, this being acceleration, this would work out to be just a negative number, and it would be a constant. It would look something like that. How do I know that? Because at any point along this velocity curve, I can pick a time interval. Here's a delta v. Here's a delta t. Delta v is negative. The velocity is dropping all the time for every delta t. So if this is negative and that's positive, then the acceleration is negative. And since this is a straight line graph, as I've sketched it, the acceleration is the same everywhere along at different times. So this is another example of seeing a negative acceleration and its consequences. When the acceleration is negative and the object is heading north, or heading up, then the velocity is slowing down. When the velocity is negative and the acceleration is negative, now the object is speeding up. So it's as if the acceleration and the velocity can work together to make the velocity speed up, or they can work against one another. If the velocity has the opposite sign as acceleration, then the object will slow down, which is more or less what we see in that graph of position versus time.